Okay, let us finish off. The chapter on eigenvalues and eigenvectors. So we can begin the next chapter, the next and final chapter. So, I'll remind you, we were solving problems about differential equations. Those are problems with the d, dx and all that business, but we were solving it not in calculus, but in the algebra way. And the algebraic way to solve these things is to look for eigenvalues and eigenvectors. And I showed you how to do this with the system of differential equations. And systems of differential equations are, in my opinion, the best way to think about these things. Systems of linear first-order differential equations. And you've done differential equations before, right? And you remember that when you've got the repeated root in the characteristic equation, that the repeated root thing, you need to do something different. Yes, John's told you about that. He told you about that thing, and that you just have to remember it, right? This is just what you do. You remember it, and you repeat that stuff in the exam, and that's what you do. Yes, you remember being told that's what you do. That's not way to live. Just do what you got told to do. But I want you to understand is why. Why do you do that? And the answer is, don't think about it as a second order ODE where you just do the thing you were told to do. You think about it as a system of linear first order ODEs. And then things make sense. And then that term that you just multiply by, it makes total sense. And there's no special cases, it just works. It works if you think about it in the right way. Now, of course, I'm conflicted. I'm conflicted because I want you to understand the spirit of the things you need to do and why you do them, because that's what mathematics is. But on the other hand, you have this exam thing you need to pass, and it's probably more efficient just to, in that case, just regurgitate the answer you get given. But, so I'm conflicted. I want you to get a nice number at the end of this thing, but on the other hand, I don't want you to think that that's what mathematics is. So let me introduce to you a second order differential equation, but I'm going to introduce it to you as a system of first order differential equations. There's kind of two ways to do that as well, and I'm tempted to show you both, if I show you both ways, and the true soul of the subject. I'm offering you the true soul of the subject, and all you want to do is talk to the person next to you. Thank you. One way to do this is so one way to take a second order differential equation and transform it into a system of first order differential equations is to just let one variable be the y, say this example, let one variable be the y, and the second variable, just let it be y prime. And then, so this, can we call this method 1? Just, it's easy to take this thing and convert it into a differential equation. Just let y prime be 1, and then it becomes a system of differential equations. dt of y1, that's just y prime, which we label as y2. And this thing, this is just y y2 primed, or y2 primed, which is y2 double, or y double prime, which according to this differential equation is just 5y1 minus 4y2. And so we can write this as a system of differential equations, and thereby obtain and solve it using the matrix method.
I need to represent this as a matrix. So this is the t of the vector of y into t is equal to 0, 1. And remember, this we'll just call the matrix A. So this is det A minus lambda I equals 0. And of course, this thing det A minus lambda I is equal to lambda equals lambda squared plus 4 lambda minus 5 is equal to lambda minus. Is equal to this quadratic, and so lambda is equal to -5 or +1. Good. Now I also have two eigenvalues. I have all, well, more importantly, I have all distinct eigenvalues. Every time an eigenvalue occurs, it occurs by itself, not with a higher power, but by itself. And whenever this happens, you're looking for one-dimensional kernels. For lambda is equal to 1, to a minus I x equals 0. The eigenvector is any basis for the space of solutions here. Remember, this is a kernel. I've written it out like this because some of you will want to solve it this way. A minus I, well, that's just minus 1, 1, 5, minus 5, bar 0, 0. Remember, this is just you know how to find kernels. You just put it in the augmented matrix, you turn the handle. And I can row reduce this very easily. That's just row 2 is row 2 minus 5, row 1. And I get -1, 1, 0, 0, 0, 0. And hopefully you know how to read out the space of solutions given to you by this row echelon form matrix. It's almost reduced row echelon form, but I'm not going to bother with the -1 business. I'm just going to leave it like that. Plus, sorry, is it supposed to be plus? Oh, it's -5, isn't it? Thank you. No, then this is minus.
In the row reduction,
yeah, but it's minus -4 minus.
No, it's just in the R2 equals R2.
Plus, no, plus. Thank you. That is a plus. Good. So this here, the presence of this non-leading column here tells me that x2, the variable known as x2, you're free now. x2, free to be whatever you like, and I'm going to give you a new name, and I'm going to call you lambda, because lambda is the traditional name given to free variables. And x2 is free, but this row of zeros tells me nothing. This row here tells me that -x1 plus the variable formerly known as x2 is equal to 0. So the solution to this equation is, let's see, x2 is lambda, and x1 also lambda, or lambda 1, 1. So lambda 1, 1. Well, I'll just call it lambda 1, 1. Yes. 1, 1's an eigenvector. Great. Notice the space of solutions here was one-dimensional, as I promised you. I promised you a one-dimensional space of solutions, and here it is, one-dimensional. How did he know that? Is he some kind of wizard? No. It's the fact that these all occurred with algebraic multiplicity 1. They're all distinct, which means you always get a one-dimensional kernel. Is any basis for solutions to this? Now this is the safe way of doing it. You put in the matrix, you row reduce, You pull out the solutions, that's all happy and nice. But because I know it's one-dimensional, I'm going to do this the fast way. A plus 5i, what is that? Negative 5. Minus 1. No, that's A plus 5i. Yeah, 1. That's positive 1. 5. That's positive 1. Since I know this is a one-dimensional kernel, it's just going to be the span of one thing. Right? One-dimensional objects are just lines, so just the span of one object. And it's really easy to find one object that works here, because you just take the second element and you put it first, you take the first element, you put it second, and you negate one of them. So I could put the 5 here and maybe a negative 1 here. And this is going to work. And you can verify that it works. And this is a really fast, kind of by observation, if you like, a by observation method of finding the eigenvector, which is nice because it doesn't involve row reduction. So A times 1 e to the 1t plus B Notice that the top row of this equation gives you A e to the t plus B minus B e to the, and y2 being the second row. This is just y, and this is y prime. Notice that the first row just gives you y, the solution that you might have got if you just did this the calculus way. And the second row gives you the derivative of y. Yes? You can be asked to do it this way. And of course the solution in calculus is just a two-line solution. But you have to memorize. This is the way that if you go on to do a course like in computer graphics, this is the way you'll end up doing it. And this information, I mean, the calculus solution gives you this. This information here is actually very useful to you. This is the next derivative. And if you wanted more derivatives, you could just get more derivatives, and they just end up being the solutions to this equation. This algebraic and purely mechanical solution to these equations. So this is not throwaway junk that you just managed to pick up along the way. It's actually the next derivative. And if you had more variables, you can get more derivatives, and thereby create nice, smooth things. Anyway, what I'm trying to get across to you is that the second order differential equations are really just nested linear differential equations. And if you want to know why, you have to, when you get repeated roots, you have to multiply by the variable. It's by this process of taking your differential equation or your second order differential equation and writing it as two nested linear differential equations. In this case, the you take the derivative operation. It would be d minus, what is it? What's my factorization here? D minus 1 d plus 5 y equals 0. what you would do is you'd solve this equation. And this would just be D is just dt, the differential operator. You just solve this equation. It will end up giving you a solution. You could call that solution U. And then you would take that solution, call it U, and then solve this differential equation. And you could do this with any number of differential equations. The point I'm trying to say is if you do it this way, as a sequence of differential equations, then everything is just mechanical. You don't have to memorize anything. But maybe it's more efficient for you to memorize it in the final exam. So the conflict. Anyway, probability. Allow me to tell you a story about probability. So, I remember when I was in your shoes, someone told me, Daniel, don't do probability. Probability is the worst. And I listened to this person, and there was a second year course in probability that I absolutely just left to the last minute because the person I spoke to told me not to do that subject because he really hated it. And so, at the very end of my degree, I finally enrolled in probability. And it was the greatest. The probability course I did was amazing. And I loved every moment of it. And I thought, why did I leave this till now? It's too late. I've done my degree. And this is the only chance I get to do probability. It was awful. So I encourage you not to be afraid of probability. The other thing I want you to know about probability is that, yeah, it's about numbers, but that's only half of the story. In a former life, I used to play a lot of poker. And poker's fun. And I used to make a bit of money out of it. It's more, you don't just count cards, you need to play the people. You don't play the game, you play the people. So in the circuit, there was this guy called HH. And everyone hated HH, all the regulars hated HH. HH was a mean, nasty cheater and bully. We all hated HH. He'd just turn up all the time. Everyone else got along reasonably well. And HH was a jerk. Anyway, it's the first hand of the night. I'm in because I'm big blind, and I've got this rubbish. I've got like 10-6, but I'm in anyway because I just have to be, just where I sat on the table. HH is in, and the cards come out, and I'm on top pair. I'm like, okay, I don't really care. It's a pair of 10s. It's nothing, right? I'm not going to get excited about this. I just check it, or I put a small bet on just because why not? I got a pair of 10s, right? And I think I checked it actually, because HH puts like half his chips on the table, and I know this move. This is the move you make when you just tell everyone, I'm taking it. I'm just going to muscle you all out of this measly. It's like 100. It's 100 on the table, and he's like, I'm taking it, and screw you all, I'm taking this, is mine now. And it's a bully move from the bully guy. And I'm thinking to myself, he's just being a bully. He's just trying to muscle everyone out of this amount of money. And you know what? I'm on top pair. So I checked it earlier, and I just go all in, realizing that this guy is a bully, and he can't possibly back down because that shows weakness. And I've got him hook, line, and sinker. And of course, he sweats on this for a moment, but he does go all in because that's just the way he is. He's got nothing, and I've got nothing too, but my nothing is slightly better than his. The rest of the cards come out, take him to he's gone. He's gone for the night. And I didn't end up winning that night, but the emotional victory was amazing. And we were rid of HH for the whole evening, which was great. Everyone just wanted to buy me a drink because I got rid of HH. So probability. Probability is what lets you read people, because you don't. It's not enough to. It gives you that extra information. Does this person like to play risky? Does this person like to play safe? Is this person a bully? All right. It's the way they respond to these probabilities that gives you that information. So you're going to learn about the numbers, and I encourage you not to just think about the numbers, because it's not all about numbers. It's about people and how they respond to numbers. For example, I've got all this I've got all this insurance. My wife insists on having insurance because she just wants insurance for everything. We've got insurance in case our place burns down. We don't even own the place. She just insists that we have insurance because of fire, because she just has to have it. And so while in my mind I'm calculating the probabilities and saying we'd be better off just keeping the money in a bank account and saving it in case something does go wrong. No. Shut up with your probabilities, Daniel. We're just doing this, and that is the right decision. So, probability. Probability affects lots of things. We're going to learn about the language of probability in this, and then we're going to do some, essentially counting is all it is. Just counting. But we're going to count in some ways that perhaps you've never counted before. The language that we need is fundamentally this notion of set. A set. Now, I encourage you to contrast the definition of set with any other mathematical definition you have encountered so far. And the definition of set is a bit wordy and vague. And that's how it is. That's how it is. The science of mathematics is not able yet, and perhaps it's impossible, to mathematically define set in the same way as you define things like a right triangle. So we have the definition of set, and as unsatisfactory as I find it, here it is. A set is an unordered collection of objects. I prefer to think of it as a bucket. It's a bucket. You put things in the bucket, and you can look in the bucket to see what you've got. There's no order to the objects in your bucket. Here is my bucket. It contains objects. There is no order to my bucket. And the only thing you can ask of your bucket is, do you have an object inside? And so you could ask of your bucket, do you have a green pen? Yes, you do have a green pen. And you would denote that. Green pen. I got all colors of pens. I got a whole rainbow. You write that mathematically in this notation, where you say this means A is and this is the language we use. A is an element of. I ask my bucket, do you have a red pen? No, it does not have a red pen. No applause. And you write it with this way, where with the element of business, this literally means element of, with a stroke through it. So this means A is not. Or big A. To indicate it's not in there. Now, the nature of our bucket, where you can only, I guess, look at it is not the right way. You can just inquire of it, as if an oracle. You can say, "Oh, bucket, do you have a black pen?" And it responds, yes or no. Right? It doesn't tell you that it's actually got loads of black pens, and it doesn't tell you anything about the order of the objects in the bucket. It just says yes or no. And that is the nature of sets. So we can talk about the set with or bucket, I prefer, of all of which contains A, B, and C, and will respond yes to you if you ask it, "Oh, bucket, do you have A, B, or C?" And you could write it this way because it doesn't care about the order, and you could write it this way because it doesn't care about multiplicity. The bucket doesn't tell you, yeah, I got loads of black pens. No, it just says yes. So it doesn't matter if you repeat elements here. The responses from the bucket will be the same. Notice that we would distinguish between the bucket which contains a black pen as a mathematical object in its own right, and we would write it as say like this, the bucket which contains a black pen, and we would distinguish from that a black pen, which would be written like that. So an object, and the set which contains that object would be mathematically different things. And it's purely just mental construct. Do you consider it within a bucket, or do you not? Right? And as much as that's just something we make up, we are going to distinguish between the object in a set and the object not in a set. Okay. You can have a bucket with nothing in it. And we denote that sometimes by this, or we can call the brace and just close the brace like that. Being the bucket, the start of with no elements listed inside. Now, when we're talking about counting and probabilities, we're usually talking about something specific, like hands in poker, and you may particularly want to know which hands in poker would beat my hand in poker. You could be talking about people who attend UNSW. You could be talking about a population of people in Maths 1231. When you declare, when you're talking about probabilities, you're usually it is helpful to be precise about what you are talking about, and you declare your universe to be that set of elements. So the universal set is a set of elements that we're interested in. You're talking about students at UNSW, then you declare your universal set to be students at UNSW. You're talking about hands in poker, you declare your universal set to be hands in poker. Things make more sense this way. Personally, I like listing the elements in my set. I like being very clear about what's in my set and what's not in my set. Thanks to our Greek tradition in mathematics, we don't only do it that way. We also like to say, here is a set of objects and I'm going to declare them and define them by properties which I insist they have. This is very different. For example, the way this normally goes is these objects. So you set it up like with the braces, then the family of objects, and with these properties. The family of objects is So the family of objects, for example, x, this should really be x, is an element of the real numbers. So this set here, S, x is a real number, saying we're talking about the family of real numbers. That's my universal set. Not students at UNSW, but real numbers, where x is also an integer. So from this universal set, with these additional properties that x must be an integer. That's my set S. Or I could talk about x from the real numbers, such that x is strictly between 3 and 5, and up to including 5, being a subset of these family of real numbers. You could also talk about a set of real numbers such that the number squared is less than 2. And this is the kind of silly situation you can sometimes find yourself in, where you insist that your numbers have particular properties, but in fact numbers with such properties do not exist. So when you're defining your sets in this way, it's not necessarily clear that anything satisfies those conditions. Okay, so subsets. We've kind of hinted at this already. A set A is said to be a subset of B precisely when every element of A is also an element of B. And we use this notation, which is kind of similar to the less than or equal to notation. Notice that less than or equal, we have less than or equal to, and we have strictly less than. This is called a proper subset. And it means that B has strictly more stuff than A. B's got A covered, if you like. Everything that A's got, B's got it too. Now, this one here means B has got A and more, and definitely more. Some stuff that B's got, A hasn't got. And this one here means A's got B, B's got everything A's got, and potentially nothing more. Potentially it could be equal to A. So this one here means A is a subset of B, or A could be, in fact, be equal to B. And this one here means that A is a subset, well, yeah, this one here means that A is not equal to B. B's got some stuff that A doesn't have. Example. Here is a set, and here is another set. Prove that one is a subset of the other. Now, being Babylonian at heart, I don't like things being defined in terms of these properties. I like things being defined in terms of lists. I like to see the elements. A defined like this, I don't even know if A contains anything. Written like this, it's not clear. I like to see the elements of A, and I like to see the elements of B. And this is what I encourage you to do when you're encountering a set for the first time. Try and get a feeling for what this thing actually contains. So, observe, just for our own benefit, that A is equal to, okay, A, what kind of stuff have you got? Well, when K is equal to 0, it's got 3 times 0 plus 1, which is 1. When K is equal to 1, it's got 4. When K is equal to 2, it's got 7. When K equals 3, you've got 10. When K equals 4, you've got 14. And so on. Extra stuff as well. And in the negative direction, when K is equal to -1, you've got -2, -5, and so on. Extra stuff as well. So here's just some stuff that A contains. It's got more stuff, but I like to see what kind of things A contains. And B, what have you got? Well, when K is equal to 0, it's got 4. When K is equal to 1, it's got 10. And then it's got 16 and other stuff. And when K is equal to -1, it's got -2 and other stuff. Now, let's have a look at the elements of these things. B's got a 4 in it. A's got a 4 in it as well. B's got a 10 in it. A's got a 10 in it. B's got 16. Okay, turns out A has 16 as well. Does it? Hang on a second. Thank you. I was worried there for a second. Okay. And the -2, it's got the -2. But A has a number 1 in it and B does not. So there's definitely everything that's in B also in A. But there's some things in A which are not in B. In particular, 1 is an element of A, but it's not an element of B. This is to me, that looks great. And I'd be happy just to say, therefore, B is contained in A. But that is, alas, not what we're after here. What you need to do is use the definition. So assume this is what you must do. Well, that technically just proves this. So to prove B is a subset of A, you must take any B and show that it is also an element of A. So if B is an element of big B, then, okay, so I get my bucket and I take out an element of the set, any element. Now the only thing I know is that it has a particular shape. Then B is equal to 6k plus 4. K is an integer. It has this shape. Now I need to bash this shape so that it matches this shape with my powers of algebraic manipulation. The first thing I want is this 1 here. It's supposed to end in a 1. So I'll break this 4 out so that it has a 1 in it. So this is 6k plus 3 plus 1. Okay, so far so good. I've got the 1 that I need. Then it's supposed to be equal to 3 times something. And look, a common factor of 3. This is equal to 3 times 2k plus 1, which I'll then write as 3j plus 1, where j being j being equal to 2k plus 1 is an integer. And behold, I have shown that this number here, 6k plus 4, can be written in this way as 3 times an integer plus 1. So B is an element of the set A. This number has the shape 3 times an integer plus 1. If you like, it's just 1 off a multiple of 3. To show that, we might say that B is not equal to A since 1 is an element of A, but 1 is not an element of B. For this course, I think it's sufficient to do this. Some of you are doing discrete maths, yes? If you're not doing discrete maths, cancel whatever it is you're doing next semester and enroll in discrete maths, greatest subject there is. And you'll see a more formal way to prove this. I think it's appropriate for us just to list out the elements here. And if you see something that's in here that's not in here, great. That'll do. That'll do. Okay. Some set operations. Some of you are familiar with these operations already, and you've seen Venn diagrams. You might remember Venn diagrams, yes? Yes, you remember Venn diagrams? Cool. I think that's the appropriate way to understand what we're about to do with these set operations. Yes, those of you in discrete mathematics will understand these things more formally. For us in 1131 and for the purposes of probability and counting, Venn diagrams, just as good. Okay, so you can talk about the union of two sets. I have my buckets, A and B, and I take my buckets and I tip them into a new bucket. And that bucket is called the union of A and B. It contains everything that A had and everything that B had. I will draw it for you. So it's everything in A and everything in B. This box I'm using to denote the universe. So you can imagine my universe. I declare it to be the students at UNSW. Set A would be students studying mathematics. Set B would be students studying physics. And we could talk about the students who study mathematics or physics, which would be represented by this shaded region here. The intersection. Again, A, B. The intersection. Now, I take my buckets, and all I want is the stuff that is common to my two buckets. So I don't tip them into each other anymore. I just inquire, what elements do you have bucket A, and what elements do you have bucket B? And I make a new bucket which contains those things which are in both, shaded in this way. The things that overlap. If you like, these, to continue our analogy, the students which are in both A intersect B, both physics and mathematics. So you might have seen these two already. Here's something new. A, B, the set difference. From A, remove everything that is in B. This is my bucket A, and I'm going to go through my bucket B and remove everything that is common that A has that B also has. So I go through. Perhaps the best way to do that is. So I have my bucket like this, black pen, red pen. This is A, this is B, and I go maybe like this, yeah. And I say, okay, here's my set A, here's B. B contains a black pen. All right, I'm going to remove all the black pens from A. B contains a blue pen. I'm going to remove all the blue pens from A. Of course, it's already done. There are no blue pens to remove. And thereby, the thing that's left is just the elements of A which were not common to B, which is this region. This is called the set difference. A remove B, if if you like, if you want to say it in words. The complement. This is why it's important to define your universal set. We haven't really seen why it's necessary at this stage. Here's the set A. And here is the set of things which, there's S. And here is the set of things which are not in A. Another way to define this, and maybe even a preferable way to define this, is it's the universal set. Remove all the elements of A. And if two sets are disjoint, disjoint sets look like this. There's A, there's B, and they don't overlap each other. This is what it looks like. Two sets. Normally when you draw your Venn diagram sets, they kind of touch each other. But if you're talking about sets which are disjoint, they don't touch each other. Okay, so let's do some examples. Sorry, did you need that for a bit longer? There you go. Let's do some examples. Now, has anyone here seen Doctor Who? Is that a thing that yeah, two people. Some people have seen, yeah, some people are, yeah, I've seen Doctor Who. All right. For those of you who haven't, Doctor Who goes to all sorts of different universes. And that's exactly what we're going to do right here. In fact, that's what you do every time you start a question about probability. You have to define your universe, and in some questions, especially when we get to conditional probability, we're going to start in one universe and change to a different one. And mathematically, this is very easy to do. Here, we're going to just declare that the universe is S. Everything else in the world is gone. You only see S. Nothing else exists, just this. Within the world, there are some collections of events. A is the collection of objects, of events 1, 3, and 5. B is the collection 1, 2, and 3. To continue our analogy of, say, students at UNSW, or maybe poker hands, you might consider the universe of poker hands and ignore everything else. And the event A would be the hands which beat your hand, and the event B might be the hands which lose to your hand, or something like that. These correspond to things which are happening in the universe you're interested in. You could talk about A union B. So either this thing happens or this thing happens, and that gives you the collection of things which are both in A and B. What you're doing here is you're taking your buckets and you're tipping them into each other. And of course you could get all the elements of A and all the elements of B, and just write them together. And this is the collection, A union B. But it's a somewhat inefficient way of writing things, because I've repeated writing the number 1, and I didn't really need to do that because it's a set. And I've repeated writing the number 3, and I didn't really need to do that because the set only cares about instances. It doesn't care about multiples of instances. It doesn't care if you add the number 3 1,000 times. When you ask the bucket, do you have 3? It will say yes. It doesn't matter that you've added it however many times. A intersect B, that's the things that are common to A and B. So you just go through A and B and you look for the stuff that is shared. 1 is shared, 3 is shared, 5 and 2, not shared. And so the intersection is just those things. The set difference. The way you compute the set difference is as follows. You start by progressing through B, not A. You start by progressing through B. And you go through B, and you just cross off everything that A contains that you find. So you start off with 1. A, do you contain 1? Yes, you're gone. A, do you contain 2? If you did, it would be gone, but you don't, so I'm not going to do anything. B contains 3, A contains 3, it's gone. And then you're done. So A contains all that's left. the things that are left in A, once you've removed all the elements of B, just 5. Similarly, you can progress through A, you can remove all the elements of A from B. You just enumerate the elements of A. B contains a 1. B contains a 3. And you try and remove a 5 from B, there's nothing to do. So all you get left with is the 2. The complement, a complement is the universal set minus the set A. So you just progress through this thing and you progress through the universal set and remove the elements of A. So you've got a 1, remove it. You've got a 3, you've got a 3, remove it. You've got a 5, remove it. All that's left are the 2 and the 4, which is that. And similarly for B complement is the universal set minus 1, 2, 3, which you just progress, remove 1, 2, and 3, bang, 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 all that's left is 4, 5. Okay. There are set laws. The set laws define the way union and intersection and complement behave with respect to brackets. Some of you have done discrete maths all over this stuff. Great. I'm tempted just to leave it until we need it at this stage, because I think there's a lot of definitions so far, and you're probably just hankering for something real rather than me just giving you more definitions. So okay, I'll do that. We've described so far the sets, the notation around sets. What we're really interested in is measuring the sets. You see, the sets correspond to events or things that have happened in the universe you're interested in. For example, hands that beat your hand at poker. You'd be very interested in that number or measuring that quantity. And that's what we do with this notion of size. So if A is a set containing some elements, then we put some bars around it, like the absolute values, and this means the number of elements in that set, or the size of that set. For example, if A is the set of letters in the English alphabet, the size of A is 26. If A and B are disjoint sets, then the size of, remember this is what disjoint sets look like. Then if I want to know what's the size of this thing, well, I could say it's just the size of A plus the size of B. In general, your sets don't look like that. In general, sets kind of overlap with each other. So how do you count the number of elements in this case? The best way to think about this is, of course, with a Venn diagram. Yes? I will now count for you the size of the union of A and B. If I want the size of the union, then the first thing I might do is just say, well, it's got to be everything in A, right? And I've counted at this stage this much of the overlap. And then I say, okay, and it's got to have everything in B in it. And I've counted at this stage this much of my set. Oh dear. But this stuff in the middle, this stuff here got counted twice. This stuff here got counted once when I added the elements of A, and it got counted again when I added the elements of B. And remember this area, this region here is called the intersection. So everything that's in the intersection got counted twice. So to remove that double counting, I remove the size of the intersection. This is called the inclusion-exclusion principle. Some of you have heard it already. If all that stuff with the definitions and sets and the elements of and the complements and the Venn diagrams, if that was doing your head in, and your head only has space for one thing in this hour, make it this thing. This is the one thing that your head that I want you to make space for. Of course, if you can fit more than one thing in, great. But if it's only one thing, make it this. For example, how many integers are there between 1 and 100? Oh, so which are multiples of 3 or 5? Okay. S is my universal set, and it's the integers 1 to up to 100 inclusive, between 1 and 100 inclusive. Let's A, B, I like to define my sets in words, and then let's see, 3, 6, 9, 12, 15, 18, la-di-da, up to 99. And this is, I like this. This is how this is all the elements here, and I've done some ... just to save myself some space, but it's hopefully clear to you what the elements of A are. The elements of B. B is the set of multiples of 5. For example, and they are 5, 10, 15, 20, so on, up to 100. Good. The question asks me how many of these are one or the other. And I can't just say, oh, well, it's all the elements of A plus all the elements of B, because some of these things are repeated. I would double count all the multiples of 15, in fact. Some of them are both multiples of 5 and multiples of 3. And so I must use the inclusion-exclusion principle. A union B, the size of A union B is by the inclusion-exclusion principle. There's all the multiples of 3 plus all the multiples of 5 and minus the multiples of A intersect B. Now I need A intersect B. A intersect B is of 15. All the multiples of 3 and the multiples of 5, otherwise known as the multiples of 15, and they are 15, 30. Good. So, what do I have here? The size of A, there are 33 elements in A. The size of B, there are 20 elements of B. And the size of A, minus the size of A intersect B, there are 1, 2, 3, 4, 5, 6. 6 elements in the intersection. And therefore the answer is 47. 47 elements, 47 numbers between 1 and 100 are multiples of 3 or 5. Maybe that's a good spot to leave it. Maybe that's a good spot to leave it. So let's pause there for today.